All right, let's talk a little bit about this precise definition of limits. And this is definitely one chapter that if you don't necessarily have maybe like a 100% total grasp of what's going on, that's okay. This is just kind of a way to introduce you to the concepts here, especially if you go on in math and you take some more math classes, um, like especially in analysis or things like that. You're going to use this quite a bit. So for now, if it's just kind of get an idea and a feel for it. I typically don't test over any of this material or have it in quizzes or anything like that. So uh, it's sort of more of a way to expose you to the idea, but you don't really have to have like 100% mastery of it. So, all right. Well, let's take a quick look. So this definition requires a little bit of explaining. So, say we have the limit as x approaches a of f of x equals some value L. And that looks kind of dark. Let me make this a little brighter. There we go. All right, so you have the limit as of something as it approaches L. And so the way that this is defined is you say, well, okay, well, this is true if you have the absolute value of some f of x minus L less than epsilon when the absolute value of x minus a is less than some delta. So let's kind of take a look at what this means sort of practically first, because it'll make a little more sense. You can see how and why they set it up like this if it's laid out a little bit, hopefully at least. So let's say you have some function like that. All right, and then right here you have some value of L, right? And then this value of L is going to have a corresponding value on your x-axis of A. Okay, so if you look here, this f of x minus L is just going to be some sort of a distance. And really what's going to happen is you're going to pick this epsilon. You say, okay, let's say you want this epsilon to be 0.1 or, really whatever number you want it to be. So you're going to set this epsilon and you're going to say, okay, if I set this epsilon at a certain value, what value on the x-axis or what range on the x-axis is going to guarantee that I'm going to be within epsilon, within whatever I set, like 0.1 or whatever of L on the y-axis. So what's going to happen is, we'll call this L plus epsilon and L minus epsilon. So this right here, from here, move my hand out from here to there, that's our range where if we're in that range on the y-axis, we're going to be within our value of epsilon. So if I just took these and I drew lines over, right, and I came down here, so you see now we have a corresponding, interval down here on the x-axis. So now it doesn't necessarily have to be like this, but just to kind of see what we're doing, right, we can call this we can call this A plus delta or A minus delta. So this definition says we're looking ultimately for a value of delta that if we are within delta of A, within let's say it comes out to 0.005, right? So if we're within 0.005 of A, then we're guaranteed on the y-axis to be within whatever our epsilon is, like 0.01 of L. And this interval down here doesn't necessarily have to be, you could say, well, this is, you could set this as like in here if you wanted. It doesn't necessarily have to be exactly corresponding. You're just looking for, and especially when you use proofs and it gets a little more complicated, you're just looking for any interval down here that's delta that will guarantee that if delta is typically a function of, epsilon, like you say, if I use, if I take epsilon and I divide it by 5, then I am guaranteeing that that value is going to put me within the limit that I want, or the closeness that I want of L. All right, so I hope that kind of makes sense. That's the idea of what we're doing. You notice here it's written a little bit different. You see f of x minus L, right? That's going to give us the distance, right? That's a distance formula, just like this is a distance formula. So we're looking for these distances away from L, wherever our function is at, that has to be within these boundaries that we're going to set. So let's look at an example maybe that you can kind of see how this works out. Because really what you do once you get later on, if you go on to like an analysis class or something, is you're going to want to find like a d as a function of epsilon, or delta as a function of epsilon. So you want to find some sort of equation. So let's take a real easy example here. Say limit as x approaches 1 of 3x minus 1 equals 2. All right, so this is going to be our L right here. This is going to be our f of x right here. And then this is going to be our A right here. So first off, let's start on the left-hand side, on the f of x minus L side. All right. Well, we have f of x. We know what that is, so let's write this out. Say absolute value f of x, that's 3x minus 1. All right. So we have that minus L, which is 2. Going to be less than some value of epsilon. So sort of the trick behind this is we want to ultimately make this look something like this part, the x minus a. So a is 1, right? So somehow we want to transform this to look like x minus 1 as less than some delta. So let's take a look at it and see what we can do. All right, so this is going to give me 3x minus 1 minus 2, that's minus 3. That's less than epsilon. Now, looking at this, I say, okay, well, if I want it to look like x minus 1, I could conveniently divide a 3 out. Let me move my little camera down here. I could conveniently divide a 3 out of each of these. So I'm going to say 3 times x minus 1 is less than epsilon. Now, we're kind of in business. See, I'm looking at it to be like this. All right, so one more step, and then I can be there. I'm going to have the absolute value of x minus 1, and I'm going to divide each side by 3. So this side, the 3 cancels out. Equals, that's kind of a weird looking thing with an E and a backwards. Well, yeah, okay, anyway, you know what I'm saying. All right, so now I'm looking good. I'm in business because x minus 1 is the exact same as this x minus 1. So if x minus 1 and x minus 1 are equal, then from here we can conclude that d, because we want d as a function of epsilon, we can conclude that our delta has to equal epsilon over 3. Or really it has to be, our d has to be less than, probably it's a better way to put it. But we'll kind of, for the idea, we'll set it like that. So then we know that no matter what, if I set my delta as epsilon divided by 3, that's going to give me a value. You can't really see it. Let me see if I can get. So here, remember, epsilon is on the y-axis up here. So if I set my epsilon, if I take that value, say if I want it within 1 of L, right? Well, then I know that down here I would have to do that. This corresponding would be 1/3 of this and that. And if I go a third here and a third there, then that would guarantee that I am within my chosen epsilon value, epsilon of L. So I hope that kind of makes sense. It's a concept that took me a really long time, and a whole lot of thought to sort of sit down and figure out. So again, if you don't have a complete, like 100% foolproof understanding of it, or bulletproof understanding of it, maybe I should say, then that's fine. Just sort of get used to the idea of what we're looking for here when we talk about a precise definition of a limit.